All right, let's look at some examples for Module 7. So Module 7 is looking at three-phase circuits, three-phase power systems, which pretty much all power systems are three-phase, and so we have kind of like three circuits in one, three problems in one, but if things are balanced, we can simplify it into one. But let's look at an example first of having what we call a Y connected load. So let's say we have a Y connected load, and we can draw it different ways. Let's draw it so it looks like a Y, I guess, first time. All right, and so for a three-phase power system, basically we're going to have, three lines coming cross country. We'll have them, or three phases, A, B, and C. Three phases, three lines, whatever. And so everything is going to kind of come in threes. And so we'll have three loads. We call these ZY. Hopefully you can see the Y shape here. Y sitting on its side or at an angle or whatever. But this would be the same as, you could also draw it like this. Maybe it looks a little neater. I can draw nicely. Hopefully you can see that this would be the exact same thing. We have what we call this point the neutral point. Maybe we'll call it capital N. The neutral that comes is the point where all the Y base impedances come together. All right, and again we have our lines here. So let's say we have some ZY is, I don't know, let's just say 10 plus J 20 ohms. All right, so that means if it's a balanced system, all three of the loads, all three of the three phases will be exactly the same. And so balanced means all the ZYs are equal. In general, we could have ZA be one thing, ZYA be one thing, ZYB be different, ZYC be different. I mean, when you hook up customers to a power system, everybody's houses take a different amount of power at different times, and so they could, in reality, they're often different. But lots of times we can assume they're balanced under certain conditions. So we'll be doing a lot of balanced circuits. It makes it a lot easier. Okay, let's say we want to find the equivalent. Usually we're probably going the other way, but let's say we want to find the equivalent delta. So there are two ways to connect in Y or delta. Let's make it look like a delta maybe here. All right, so again, we're going to have the same three lines, A, B, and C, or three phases, A, B, and C, and then they're going to connect up in a different combination. So this would be a delta combination. All right, so maybe we call them Z delta. Again, balanced, so they're all the same. And so if we had a ZY load and we wanted to make an equivalent, kind of like the Thevenin equivalent, but just a different kind of equivalent, a three-phase equivalent impedance bank, a three-phase bank of impedances in a delta connection, what would that look like? And let's see how we would really draw the delta over here in this kind of squarish look, something like this. A, B, and C. All right, so hopefully you can see that these are the same. In a delta, each impedance is in between two of the lines. So we have like a ZAB and a ZAB and a ZBC and a ZCA, right? In a Y, everything is connected line to neutral. So we would call this like a line to neutral impedance. The lines are the ABC, neutral here. Whereas for the delta, we would call it a line to line kind of impedance, right? And it's really easy if we have a balanced case, if we want the Z delta, the equivalent Z delta is just 3ZY. All right, to get an equivalent impedance, so that if we're kind of the same terminal idea like Thevenin, for this ABC, if it's a delta, or if this ABC, if it's a Y, it wouldn't know the difference. The rest of the system out this way wouldn't know the difference between three Y's and three deltas, as long as the delta is 3 times ZY. So very easy then, we're just going to take 3 times 10 plus J20 ohms. And so Z delta for the equivalent would be 30 plus J60. Ohms. All right, that doesn't want to go away. Okay, and so if you had to find the equivalent, you would do something like that. Let's go ahead and name all the voltages and currents just so that you can kind of get used to the convention. And so we would have 3 lines, so we have 3 currents in the different lines. We call them the line currents. All right, so IA, I guess we go with capital A, IB, IC, C. And so that would be the equivalent kind of thing here, IA, IB, IC. Generally, we draw the current coming. We would think a source is out here feeding, like the power generating plant is out here feeding these loads. And so the current's coming into the loads, the customers. We would have in the delta some different currents, right? In the line, in the Y, IA comes in, they all come in to each other. And if the neutral, sometimes there's a third wire, a neutral wire that runs through here back along in the power system, or lots of times there isn't in a 3-phase system. But so if there is no neutral wire, we would say, and if it's balanced in general, IA plus IB plus IC, what happens? They all come in, right? Equals 0. So in a balanced system, all 3 of the phase currents add to be 0. So we call a phase a branch of the circuit. So all 3 of the line currents, because the line currents are the phase currents in a Y, they add to be 0. And even if there is a neutral wire that is connected and completes the circuit, this still would be true in a balanced circuit, because the way the circuits are made, if they're balanced, the neutral current should be 0. All right, so same kind of thing holds here if it's balanced, but now we've got, notice in the one phase of a delta, right? In one phase of a delta, each phase is connected between the 2 lines, and so we can just make some new currents, IAB, the current from A, so this would be like point A, B, and C, right? Lines. And so IAB, IBC, ICA. Everything comes in sets of 3. ABC, ABBCCA, kind of going around in a circle here for the currents. Okay, and we can do KCL at this node and say, okay, well, so IA plus ICA equals IAB. In equals out, or however you want to look at it. And so there are relationships between the phase, the line currents and the phase currents of a delta as well, or the line-to-line currents, if you want to call them that. All right, so that's kind of the current names. We also have a whole bunch of voltage names, right? Let's draw the voltage names on this one, since I made kind of a mess of the currents over here. So for the line to neutral, we would name the voltage that's plus at the A line, and minus at the neutral, VAN, and then we have a VBN, and we have a VCN. Each one is positive at its line, negative at the neutral. Right? Okay. We can also name, it's kind of not really across any one element, but we could, well, let's just do it down here. When we're looking at the delta, there's no neutral, so it's kind of hard to get the VAN in here, but we can just do across the loads here. So we got VAB, and then VBC, and then VCA. So we kind of name them in a circle, AB, BC, CA, and then each of these sets is a 3-phase set, and if it's balanced, each set will add to 0. All right, and so over here we can also put the line volt. So these would be called line voltages or line-to-line voltages, right? Voltage between the lines, whereas these are line to neutral voltages, line to neutral, right? But we have line voltages over here. We've got VAB is also here, VBC, VCA going back up. We can also define them in a Y, right? And so that's probably about enough names. We have, like I said, in a balanced case, we have VAN plus VBN plus VCN equals 0. VAB plus VBC plus VCA equals 0. We have IA plus IB plus IC equals 0. We have IAB plus maybe, hopefully you're getting the pattern here, ICA equals 0. So we like balanced circuits. We've got lots of different equations that we can utilize in here. And then in general, we have, these are all phasors, complex numbers, right? And so if we have VAN here, then they're all separated by 120 degrees. So you can kind of, my picture's a little off, but then we got VBN and VCN. All right, so if you think of rotating phasors, rotating with speed, angular frequency, or angular speed omega, AN comes first, and then BN and VCN, right? They're a whole set. Or sometimes we would write VAN or VCN as ahead of VAN, or however we want to think about it. We have the relationship that VAB, VBC, and VCA, we're getting lots of things here, but so this would be VAB is 30 degrees ahead of VAN, VCA is 30 degrees ahead of VCN, and VBC 30 degrees ahead of VBN, and again, they are all 120 degrees apart as well. So we've got all these rotating phasors, each phase 120 degrees separated, line to neutral and line 100 or 30 degrees out of phase with each other. For what we call ABC kind of sequence, the positive sequence. There are some systems, if you connect your wires just opposite, you could have an ACB kind of sequence, and then you would have different relationships. But let's just go with ABC, balanced kind of system. We would have this kind of a relationship. And so we can say VAB in general is going to be VAN for a balanced three-phase positive sequence at an angle of 30 degrees. Whoops, off the screen, sorry. Okay, so that's another equation that we can use. This doesn't really have a lot to do with this one example that we've got here, but should we calculate some of these? Let's just do another example. So do practice with the names, neutral, line to line, line to neutral, phase versus line, all these kinds of things, so that you can, because that's a big part of a lot of these problems is knowing what we're talking about, what you're given, what you're asked for. Okay, so let's look at another example with a little more stuff in it, as if that wasn't enough stuff. Okay, so let's say we have a source, right, some sort of a generator. Okay, three-phase. We're going to have transmission lines that actually have impedance in them. And then let's have two loads. Let's have one that is a delta load. That's going to be a little bit of a mess trying to put these two loads in here. One that's a delta load, and then we're going to have, let's just have these come off here into a Y load as well. Okay, so these are connected in, so we've got two loads. We would call them two loads in parallel. They're three-phase loads, but they both connect to the same positive voltage point, and they are 3 points. And so they would be parallel loads, and let's just call these Z1, or I guess we'll call them ZY1. They're all ZY1, and these are all Z delta 2. This is load number 2, load number 1, even though I wrote them in the opposite things. Z line, let's say they're all the same. All right, and then we've got the source over here, and let's just go ahead and name the phases here. And so this point, capital A, isn't the same as this point. We'll call this little a. It's the A phase, but it's the downstream place. So let's give them little subscripts. So power flows from big B to little b, from big C to little c, from big A to little a. All right. Source side, load side. Okay, this one has a neutral point, but the other ones are the source. Hopefully you see the source is in a delta. These are AC voltage sources. And this load is in a delta, this load is in a Y. All right. So first, we like to have balanced systems, because if we have a balanced system, we can convert everything into Y's, and we can draw what we call a one-line diagram. So is the system balanced? To be balanced, we have to have a balanced source. And usually that's a good assumption, because we have a three-phase generator. They're a three-phase machine. All three of these windings are wound on the same big core, and it rotates. They rotate together. And so hopefully, they are very well connected, and so they will always be balanced. And so the machine is made so that when one phase, A phase comes by, B phase comes by 120 degrees later, so physically they are separated coils that cause it electrically to be 120 degrees out of phase. All right, so we have a balanced source. We need to have all line Z's equal. Line Z's equal. And I wrote Z line on all of them, so they're all the same, so that's good. And then each loads 3 Z's equal. That's kind of a hard way to say it, but so this one is, each one of these is the same exact impedance, ZY1, ZY1. All right, so each load has the same impedance in either a Y or a delta. The lines are all the same, and so that means the system is balanced. Balanced system. Yes. Okay, so if it's a balanced system, we want to draw a one-line diagram. The one-line diagram for this system would look like this. All right, and so we would be taking basically one-line diagram, which we can think of it as the A phase diagram. Okay, not usually called that, but that's kind of what it is, right? So we're going to convert every piece, the source into a Y, the lines kind of naturally in a Y, and each load into its equivalent Y, and then we're going to put it into a circuit that represents the A phase, and then we can get, because of all our relationships, everything is 120 before or after the other and all that kind of stuff, we can get the other two phases easily from solving the A phase, okay, or the one-line diagram. Okay, we need some numbers. So let's say ZY is, let's just say it's just an inductor. Let's say it's J50 ohms. And let's say Z2 delta, let's say it's 45 at an angle of 36 degrees, just something, ohms. Z line, let's just say it's just inductive. So lines they're designed to have very small resistance, but the inductive coupling we just can't get rid of. So let's just say it's J.1 ohms. Let's say that the resistance is negligible, just for making things easy. So Z line is J.1, and let's just say we have, we're given that it's not very realistic, but let's just say it's a 480 volt system, and that should be good. So when we're given numbers, say it's a 480 volt system or it's a 480 volt load, that is V line to line. So line to line is like VAB. The magnitude of V, they're telling you the magnitude of VAB is 480 volts, for example, which is the same as the magnitude of VBC and the magnitude of VCA, right? They all have the same magnitude, so we can just call it V line to line. The voltage between any two lines. So if you go out here and you put your meter, measure the voltage between any of the two lines, you should get 480 volts RMS magnitude, all right? And so that's probably, we tend to be given problems in terms of line data, because that's what you could just go out and measure. If you have the 3 lines going across country, you could measure those things. So same kind of thing, if they give you a current, it would be the line current, right? The current you can go out there and measure on a line very carefully. All right, and so in the one-line diagram, though, this voltage is VAN. VAN, right? We'd have the line is already naturally in Y, so this would be Z line, which I call J.1. All right, and this would be ZY1 and ZY2. All right, so we got convert each load into its equivalent Y, and so this is like the neutral point. And so ZY1 can come straight over, right? This is just J50 because it's already in a Y. Don't have to do anything. ZY2, we've got to get the equivalent Y from the delta, right? We had the relationship that Z delta is 3ZY, so ZY is just Z delta over 3. All right, so ZY2 is Z delta, which is, okay, we'll just write it, 45 angle 36 degrees divided by 3. And so 45 divided by 3 is about 15 angle 36 degrees. Almost. Okay, so dividing complex number in polar form doesn't change the angle, just changes the magnitude, right? So now we've got our circuit, our one-line diagram for our three-phase circuit up here that we can solve. So we can, let's put some things in here. So this would be I guess I call it IA. This would be V line to neutral at the load, so we call it V little an, which is different than V big AN, right? But both of these loads would have the same voltage. So all the power system loads are in parallel with each other. It's hard to see in the three-phase picture, but when you draw the one line, hopefully it's obvious they're all in parallel with each other. So all the customers down a line, they all connect to the high voltage side, to the voltage side, and then they connect to neutral, right? Or in a delta, but anyway, in the one line they would connect to neutral. So they're all in parallel. Okay, so let's say we want to, what do we want to calculate here? Let's just say we want to know how much, what is the S of the source? All right, and so again, when we're asked for things like this, what is S of the source? Well, which source, or how much, so usually we will be saying that we're asking for S three-phase of the source, and complex, right? So it's a complex number. So it'll be the total power that all three phases, all three of the voltage sources are producing, which, if we're balanced, we love balance because it makes things easy, it's just 3 times S of the A phase, okay? So again, this one-line diagram is the A phase, so we're just going to calculate the power of A phase, and we kind of asked for the source, so source A phase, so we can calculate power and all these different things if we wanted to. Okay, so in this case, what would be S of the source? What is S in general? We had power was PIV, but now power is SIV, so it's going to be 3 times VI conjugate. VAN is the voltage of the source, current of the source is IA, and we got to conjugate it. All right, so if we want the three-phase power of the source, we need to get VAN, and we need to get IA to calculate it. All right, VAN. How can we get VAN? They told us that the line voltage is 480 at the source. We have this handy-dandy equation here, and so let's use that. So rearranging this equation, we want VAN, and actually, when we're doing a circuit like this, we're free to pick one angle as what we call the reference angle, which would be the 0 angle. Quite often, it's easiest to choose VAN to be at an angle of 0. So we want VAN to be something, angle 0 degrees, volts. All right? This relationship is just saying whatever VAN is, VAB has to be 30 degrees ahead, because VAN is a complex number here, right? When we multiply complex numbers, we add their angles. So VAN's angle plus 30 is VAB's angle, right? But that wasn't given, so it was given that VAB's magnitude. So magnitude-wise, VAN, magnitude of VAN, which we also call V line to neutral sometimes, as opposed to V line to line, is V line to line over the square root of 3. But this is telling us also the magnitude part of this. And so magnitude of VAN then, in this case, is 480 over the square root of 3. What is that? Calculator, here we go. 480 divided by square root of 3 is 277.1 volts. Let's just go with 277 volts. Okay, So the line to neutral voltage, the source is 277 angle 0. We need to solve for the current. How can we get the current IA? Well, we can just do an equivalent impedance, right? We've got the voltage known here. We know all the impedances. So the current would be, if we think of making all these into one equivalent impedance, the current from the source would be the voltage divided by all that impedance. So it's going to be VAN divided by Z total, or Z equivalent, right? In this case, what is Z total? Well, we've got the line impedance in series with this parallel combination of the two loads, right? So it's going to be Z line plus ZY1 in parallel with ZY2. Okay? Let's see if we can see what we're doing here. Okay, we'll continue on. So then Z total, Z line was J.1 and ZY1 is J50 in parallel with ZY2, which was 15. So I'm going to multiply on top and add on the bottom. 15 at angle 36 degrees divided by J50 plus 15 at angle 36 degrees. Okay, just pulling from the picture here. Okay, some fun complex math. Thankful for good calculators. So let's put this in. So 0.1 times I plus. All right. So we'll do I times 50 times, let's get this polar form number in, 15, get my little angle symbol, angle 36, and these calculators want, when you do a polar form variable, it always wants it in parentheses like that. Okay, so that's the top of the fraction. Then I want to divide by, in parentheses, J50 plus, get some parentheses for my polar, 15 at an angle of 36. See if it interpreted correctly. So we got the J.1, J50 times 15 angle 36, J50 plus 15 angle 36. Okay. Guess I'll write down the rectangular form, but polar is good too. So we got 8.41 plus J 9.33 ohms. But let's get that in polar form. So Z total is 12.56 at an angle of 47.97 degrees ohms. Okay, so we got Z total. What were we trying to get? We're trying to get current. So we would get IA is VAN, which was 277 angle 0 degrees, divided by Z total, which is 12.56 angle 47.97. Maybe keeping a few too many sig figs, but rounding gets to be a pain. All right, so you could put all this polar stuff in there, or remember that when you divide in polar form, you divide magnitudes and subtract angles. Excuse me. So the angle is just going to be negative 47.97 amps, and then 277 divided by 12.56, 22.1. Good enough. Amps is IA. Okay. Let's say we wanted all three phases, and let's just, for practice, get all three phase current. So what is IB? What is IC? So any three-phase set, we drew the picture, where to go, of the voltages, all 120 degrees apart. A first, B comes later, C comes after that, or C is 120 degrees ahead. And so same thing works for currents. And so if IA is at a certain place, IB is going to be 120 degrees behind. So same magnitude, 22.1, but the angle is going to be negative 47.97 minus 120 degrees. Right? It's a phasor, same size, but it's lagging behind 120 degrees, right? So IB would just be 22.1, angle of what, negative 167 point, whatever. Let's say negative 168, getting too many sig figs here. Okay. Hopefully I didn't do any math in my head wrong there. I think that's good. So this is IB. IC, same kind of thing, 22.1 at an angle of A's angle minus 240 or plus 120, right? Going this way or going this way, whichever way you want to go around to get to C. Usually it's nicer to keep your angles smaller overall, so let's just do plus 120. So it's 22.1 at an angle of 120 minus 47.97, 72 amps is IC. Okay, so we just solved one phase and then poof, we got the other two without having to do much work, right? Just add and subtract 120 degrees. Okay, so we were looking for the power though. So let's do SA, source is IA VAN IA conjugate, VAN 277 angle 0, IA 22.1 angle negative 47.97 conjugate, and so S sub source A 277 times 22.1 for the magnitude, 6.12 kVA, and then the angle, we've got the conjugate makes this a positive. It's already negative. When you take conjugate of something, you make it negative of what it was, and so it's going to be at an angle of 47, let's just say 48 degrees. All right. That's one phase, right? But we want S3 phase of the source. S source 3 phase. So it's balanced, so we just multiply by 3. And so 6.12 times 3. 18.4 angle, same angle, multiplying by a number doesn't change its angle. kVA is S3 phase. S3 phase of the source. Okay, subscript naming is a little odd, but anyway, something along those. The source has to provide that much power. This big rotating generator in the power plant has to provide that much complex power to feed the losses in the transmission line, inductive losses, and the the two loads that we had there. Okay, let's so if we wanted to, if we were asked for it, we could calculate the power in each load. We'd calculate the voltage here. Actually, let's do a little bit more with this circuit because you may be asked to do that in the homework. So let's redraw the circuit. We've got VAN 277 angle 0, not amps, volts, and we've got IA. We know this is J.1 and this is J50 and this is 15 at an angle 36. All right, let's say we want to know the voltage here, VA little AN, line voltage at the load, right? We would expect that the source is holding up the voltage, right? The source is providing the power, holding up the voltage, and so the voltage is going to drop across the line and be lower at the load, right? So let's just do KVL around this. Pick one of these loops. And so we would have negative 277 angle 0, so negative V source plus IA times Z line, or J.1, right? You're doing the KVL, Ohm's law, IZ Viz, and then plus, and we're looking for VAN, so let's just write it as VAN equals 0. All right, we could have done the current times these two in parallel. Did we already calculate those two in parallel? You might have, I didn't actually calculate that separately, so we could have done that, but let's just do KVL to do it. So VAN then is equal to 277 angle 0 degrees minus IAZ line, which is 277, 0 degrees. It's just purely real. We can drop the 0 degrees minus IA is 22.1 angle negative 48. Negative 48 degrees. And Z line was J.1. All right, so we can get VAN as complex number 277 minus polar form 22.1 angle of negative 48 times J.1. And we don't like voltages and current in rectangular, so we'll just get that polar conversion thing going. So we've got 275 and an angle of negative 0.31 degrees volts. So very close to the source voltage, which is what we want. The power company has to hold the voltage at a certain level. They want the lines to have very small impedances so that you don't get very much IZ drop across the line. And so, and these are just made up numbers, but you know, maybe somewhat nice numbers. Okay, so VAN then is this. What about VBN? Same size, magnitude-wise, but the angle is negative 0.31 degrees plus 120. All right, so very close to 120 in VCN. I'm sorry. VBN is minus. So negative 120.31, and then VCN is the one that's plus. Negative 0.31, A's angle plus 120 degrees. Everything's volts. Okay. What else might we want to know? Say we wanted to know the power in this absorbed by load 1. Let's say, what is S of load 1? In general, if it just said what is S of load 1, it wants a 3-phase, so it's going to be 3 times S of load 1 A phase. So many subscripts. How can we get that? Well, we could say 3 times V little a n I A load 1, right? Because it's not IA. IA is going to split. We're going to have IA load 1. We're going to have IA load 2. Well, that doesn't look fun. We could do a voltage, or we could do a current divider. Yeah, that would work. Or we can remember that I is, oops, where'd my conjugate go? There's conjugate. I is V over Z, right? We got Viz. So I is V over Z. Little side note here. And so we can put that in here. So we got 3 VAN, again, VAN over Z. We're looking for 1, so ZY1, conjugate. All right, and so we had the other power equation. In general, we have S. Remember, we had for resistors, we had PIV, and then we had I squared R, magnitude of I squared, but we've got here magnitude of I squared Z, complex form, and we also had magnitude of V squared over, and I think I gave this wrong in class, it's over Z conjugate. I think I forgot the conjugate when I talked about it in class the first time. And so, don't forget the conjugate. And so, that's what we're working on here. So we could say S of load 1, 3-phase, is 3 times magnitude of VAN squared over ZY1 conjugate. Right, because the number times its conjugate, angle, negative angle cancel out, so we just get magnitude squared on the top and we divide by Z conjugate. So let's use this equation. So we got 3 and VAN was 277 and ZY1 is J50, but it's conjugated. So it's going to be negative J50. Okay, and so 3 times 277 squared over negative J50. Negative J in the bottom becomes a positive J on the top. How? Because if we multiply by J over J, which is nothing, right? Not doing anything to the fraction, we get J times J, which is negative 1, times a negative becomes a 1, and then the J is just up on the top. All right, so this is going to be J 3 times 277 over 50. So S, load 1, 3-phase, 3 times 277 divided by 50. 16. J 16.6. VA. Was the source just VA, or did I get a KVA? Okay, the other load must have a lot more. Oh, I forgot to square my 277. 3 times 277 squared divided by 50. Okay, there we go. J 4.6 KVA, that's better. Okay. Does it make sense that it's purely imaginary? Yes, because the the load was purely imaginary, right? It's just an inductive load. There's no real part, and it's positive, so it's an inductor, it's not a capacitor, and so that makes sense. If we did load 2, which has an angle, that's not 90 or 0, this one's angle 90. This one has angle in between, so it's going to have a real part and an imaginary part, so then the power will have a real part and imaginary part, but not this one. Okay, I guess we can do one more thing while we're here. So this line, or this impedance that we're modeling as the line, is just a loss to the system, right? We would like it to be a superconductor and have 0 resistance, 0 inductance, and just everything that comes through, nothing gets lost. But we're going to have some loss, and so we can say, we don't want to say P, we want to say S, because actually there's no P because it's a purely imaginary thing. So S loss, A phase, is going to be what? Well, it's just going to be I squared R. I squared Z. Magnitude of I squared Z. So let's just use that. Magnitude of IA squared times Z line. All right. And so if we want to get S loss 3-phase, it's going to be 3 times S loss A phase. Right, again, because it's balanced, everything, all these times 3, all these magically adding and subtracting 120 degrees is all good because we're balanced. It's going to be 3 times, I guess we'll rewrite it, IA squared Z line, which is 3 times magnitude of IA was 22.1 squared times Z line, which is the J.1. Okay, so 3 times 22.1 squared times 0.1, 146. So S loss 3-phase is 147 actually, 147 J 147 VA, which compared to the other being KVA, that's a good sign. So, but it's still, it's a significant loss, and it's all reactive. So the power system is sucking VARs from the system, and much smaller, the way I did it, with no resistance in the line, so then there's no loss, real power lost in the lines, but in practice there is some. Okay, that's good for that one. Hopefully we appreciate when circuits are balanced, but let's look at an unbalanced case, because that is the reality of most power systems are unbalanced. But let's say we have a balanced source, so at least we've got that, balanced source, and we have a line. Actually, we're going to just ignore, should we ignore the line? Should we put impedance in the line? I guess let's just go ahead and do Z line is, let's just say it's J.1 again, J.1 ohms, and it's balanced. But then we have two loads. One is balanced, number one, balanced Z1Y equals J50 ohms. I don't know, something. And so is that what we had before? Well, we'll go with it, pretend the same load. But now our second load, this is number one, but let's say number two is only a single phase load. Single phase between A and B, and let's just say it's Z2 is just 100 ohms. Okay, so it's not really a delta, it's between the two lines, A and B, but there's only one of them, so it's not a delta, it's just an open thing. So how would we draw this? So let's just go ahead and draw the source as a Y to start with. All right, and then we have the line, 3 lines. So we kind of have our capital A, B, and C, and then we'll have our little a, B, and C. These are Z lines. VAN, for example. And then our first load is a Y. Even though it's load 1, let's put it down the line a ways just so it's easier to draw the second line load in here. So let's just say this is load number 1, ZY1, ZY1, ZY1. So this is load 1. And then load number 2 is just in between A and B phases, and it's just 100 ohms. So this is going to be Z2 equals 100 ohms, a purely real load for some reason. It's a resistive heater or something. I don't know, but it's there. Okay, so everything was good, everything was balanced until the second load came in and connected to like only one phase of a delta. All right, so now a lot of the balanced stuff goes away. We can't do a one-line diagram anymore. We have to solve the whole big circuit to get stuff. We were told we have a balanced source, so we can still do the balanced things with the source. So if we have VAN, we would have to be told what the voltage is of the source. Let's just say it's a, let's just say it's a 120 volt source. I don't know. Well, that doesn't make sense. Let's say it's a 208 volt source. 208 volt source. Again, when they tell us just a source in a three-phase system, this is going to be V line to line, or like the magnitude of VAB. And so VAN then is going to be V line to line over square root of 3 magnitude-wise, and let's just go ahead and make it be at 0. Probably a good idea. I think it works. So it's going to be 208 over square root of 3, angle 0, which 208 divided by square root of 3, I think is 120. Oh, come on. Yep, 120. All right, so VBN then, Since the source is still balanced, the generator is still pushing out good balanced stuff, but the loads are taking different amounts per phase, and so they're going to make the currents not be balanced. But we got negative 120 for BN and VCN, 120 at an angle plus 120. Okay, so the source is still balanced, other stuff not so much. So what can we do here? So we got all our sources. We can draw things in here, VBN plus minus VCN, just to keep track of where things are. Oh. So to solve this, it's going to be much messier. I don't know if I want to go ahead and do the whole thing or not. So if we were doing this with a line impedance given, we would have to basically do mesh currents, right? We have, call this maybe I1, this one I2, this one I3. We have 3 mesh currents, and so we can write our KVL around here, negative VA, so for example, negative VAN plus, we just call it I1 Z line. And then if we come around this loop here, it would be plus I1 minus I2 times Z2. Right, I1 is agreeing, I2 is going up. And then come back around this side, we would have plus I1 minus I3, yes, times Z line, plus VBN, and come back equals 0. Okay, this is loop 1. And then we do a similar thing for loop 2. Right, so let's start down at this spot here. So we're going to do I2 minus I1 times Z2 is the voltage plus to minus here, and then coming around this one, we're going to have only current out here is I2, so I2 times ZY1. Then back in here, we're going to have plus I2 minus I3. I3 is the current around this whole big loop here, so I2 minus I3 times ZY1. And then we've gotten back to where we started, equals 0. And just for good measure, let's do loop 3. Let's start at the neutral, I guess. So we got minus VBN plus current in here is going to be, we're going with I3's loop, so I3 minus I1 times Z line. Come over here to this one, we're going to have I3 minus I2 over here times ZY1. And then on this outside branch, we just have I3 times ZY, another ZY1. And coming back through here, again, I3 is the only thing in this outside line, so I3 times Z line. Hit VCN, run out of room, plus VCN. Finally back to neutral, equals 0. All right, so when we have something like this, we're very glad we have people who have written sophisticated computer software that will solve these circuits for us. But we have 3 equations, 3 unknowns. They're complex. It'd be a bit of messy algebra, but we have just the 3 currents that we don't know. We know all the other things, and so we could theoretically solve it. But we say yucky to unbalanced, right? One thing that could simplify the circuit a bit and make it not quite so bad, actually a lot easier, is if we ignore the impedance of the line. So let's just go ahead and look at that example for a minute. So let's say that our lines are 3 lines that has no resistance or no impedance in them. And so we're just going to have the loads directly connected to the source. So we've got VAN, VBN, VCN, is the same, is the voltage at the loads also, right? So this voltage here now is also VAN because there's no drop across the line. So this point, this node is all the same, and then the neutrals, we can assume the neutrals are connected, or the voltages, let's go ahead and assume that, let's go ahead and put a neutral in there as well. And so then we've got VA to neutral connected, neutrals connected, so it's the same neutral on both sides, and we've got VBN and VCN are also the voltages at the load. Load, this was load 1, had balance ZY1. So load 1, if it's directly connected across the source, assuming the source is ideal, it's balanced, right? Its impedance is balanced, it has a balanced source, so its currents IA1, IB1, IC1 are going to be balanced, all right, because they're balanced voltages, balanced impedances, so for this load it'll be balanced, but the source will not be balanced because it has to provide some current here, we'll call it just I2, to load 2, all right? And so in this case, we can do some calculations and get the currents fairly easily. So for load 1, for example, we can do IA1 is what? Well, it's the current in A phase, voltage of A phase is VAN, and the impedance is ZY1. And that's it. We've got the voltage across it and the current through it, so we can just calculate the current the impedance of it, so we can calculate the current directly. So it was 277 angle 0 degrees divided by J50, right? We got the stuff. And so IB1 VBN over ZY1, 277 angle negative 120 divided by J50, similarly IC1. Plus 120 over J50. So again, you can see we could have just calculated IA and then just subtract and add 120 degrees to get IB and IC. Should we do that? Let's just 277 divided by 50 is 5.54 angle of 0 minus 90, so minus 90 degrees. And this one will be 5.54 angle of negative 120 minus 90. So anyway, it'll be, or negative 90 minus 120, so negative 210. That's okay, I guess. Excuse me. And the C phase, same magnitude, 120 minus 90, so 30. All right, so we got IA1, B1, C1. How about I2? So since we neglected the line impedances, its voltages, we can do a little KVL around here directly, right? So we can say negative VAN plus I2Z, I'm going to call this Z2, I2Z2, coming around here, and then we're going to have plus VBN, back to neutral, equals 0. All right? And so that kind of comes to another kind of standard equation here. Whatever we have here, if we wanted to know the relationship between VAB is the voltage between lines A and B, right? VBC, so forth. And so in general, VAB is VAN minus VBN. Just doing KVL around here, negative VAN plus VAB plus VBN equals 0. And so VAB is VAN minus VBN. You can do the same thing with the other two line-to-line voltages. VBC is VN minus VCN, and VCA, VCN minus VAN. Okay, just in general, you can do that. And so we could have just said, well, this is VAB, and so it's going to be VAN minus VBN, or we can just, it's probably easiest to just leave it as that. So I2 is going to be VAN minus VBN over Z2. And so 277 angle 0 minus 277 angle negative 120 volts, these are volts, divided by Z2, which was just 100 ohms. I'm running sideways, sorry about that. Okay, so we can plug that in. 277 angle 0, so it's just 277 minus, get some parentheses, 277, get the angle symbol, negative 120. And then put all that in parentheses and divide by 100. I think that looks good. And let's put it in polar form. So I2 is 4.80 angle of 30 degrees. Okay. I don't know why I put a box around that, but anyway. So say we wanted to find the line currents. So what is IA? We're looking at KCL here. IA comes in, and IA1 and I2 come out. So IA is IA1 plus I2. All right, so it's the 5.54 angle negative 90 plus this that we just got, 4.80 angle 30. All right, how about IB? IB, we have IB1 coming out, but we have I2 coming in, so it's going to be IB1 minus I2. All right, so 5.54 angle of negative 210 minus 4.8 angle 30. All right, and then finally, let's save a little space here. What is IC? We're looking up here. IC is just IC1. All right, so the 5.54 angle 30. Okay. If we wanted the total power of the source, we would have to get all three pieces, do all three pieces at once. So like if we want S3 phase of the source, is going to be S A phase plus S B phase plus S C phase, because they're all different now, right? And so we're going to have VAN IA conjugate plus VBN IB conjugate plus VCN IC conjugate. And we have all these things. So 277 angle 0 times 5.54 angle negative 90 conjugated, 277 angle negative 120 times IB. Actually, I don't have it all calculated. Whatever IB was, conjugated. Hopefully you get the idea. 277 plus 120 for VC. IC, whatever IC1, we got that one. Screwed up here. Sorry. We don't know IA. We don't know IA either. IA conjugate. IA is this stuff, right? We do know IC, which is IC1, but I'll just leave it in general. Okay, so unbalanced, got to do everything separately. Sometimes if the source is balanced, it can help with holding the voltages balanced, and you can get some of the loads to still be balanced. But if you have the line drop, impedance in the line, then it's going to be a mess. Okay, well, hopefully that gives you some practice with all the names for all of these things and the relationships, practice with the relationships between them. We'll go ahead and stop there.